Okay, hello everyone. Today I'll be presenting a very interesting IPS 2023 paper titled Learning to Dive in Branch and Bound. It's by Mark Pauls and Andreas Cross from ETH Zurich. So let's quickly dive into the paper. So the paper focuses on solving mixed integer linear programming or MILPs more efficiently by using machine learning. Now MILPs are used in real-world applications, logistics, scheduling, load balancing, even verifying neural networks. The idea here is to improve a special part of the MILP solver called the diving heuristics. Instead of relying on rule-based logic to guess which variable to tighten, the author proposes a learned approach using a graph neural network. This model is called L2 dive learns from past MILP solutions and guides the solver better, saving time and gives better results. At first, it sounds like a very niche. It's like about with solving mixed integer linear programming more efficiently. But truth is, it touches everything from load balancing again to logistics, scheduling, and neural network verification. It's core industrial optimization. The key idea is to replace manual rule-based heuristic used in solver with learn GNN-based policy. That's bold, replacing solver logic that's been tuned to for decades with a neural network. I had to see if this really worked. So next, I have quickly let's introduce what is mixed integer linear programming. So mixed integer linear programming involves optimization problems where some decisions variables are restricted to integer variables. These problems are prevalent in various industries, including logistics, scheduling, and even in verifying neural networks. Traditionally, MLP problems are solved using branch and bound algorithms. This method explores the solution space by branching into subproblems and bounding regions that cannot contain the optimal solution. However, the efficiency of this method heavily relies on the heuristics used to guide the search. This is where diving heuristic comes into play. They simulate a depth first search in the branch and bound tree, quickly finding feasible solution by iteratively fixing variables and solving relaxed problems. So this innovation is the in this paper of L2 dive, which employs graph neural networks to learn effective diving heuristics from past MLP instances. By doing so, it significantly improves the efficiency of the branch and bound algorithm. So MLP used for neural network verification and server load balancing is showed in these images here. Okay, so next. Um, Let me now explain how diving works, and in the context of branch and bound algorithm, which is the heart of the solver for mixed integer linear programming. So on the left hand side, what we see here is a branch and bound tree. This represents how the solver explores different solutions, the optimization problem. Each node in the tree is a subproblem here. The black nodes are active. The solver is still exploring those parts. The gray and red nodes are pruned here, and meaning the solver realizes they can't lead to good solutions, so it keeps them to save time. Where does diving come in? Sometimes instead of branching in multiple directions, the solver decides to dive that it goes down the single path deeply, one variable at a time, to try and quickly find a feasible solution. So just imagine the solver is wearing diving goggles. It's diving down into the solution space, hoping to find treasure. That is a good solution. So the solver starts with a relaxed LP here, a linear programming version of a problem, which ignores integer constraints. It solves that and gets a solution. Okay, then it picks a variable. And fixes it to an integer value, either up or down by floor or seal. We can do it in Python. The narrow the problem, we can call it updating the bounds, called creating a new subproblem called p prime here as it's given in the equation. Then the solver resolves this LP again. This is fast and it keeps doing this step by step, going deeper. And mathematically speaking, the solver tries to solve argmax equation, argmin equation, and a modified version of LP with tighter bounds. And I can say the solution, so the LP solution is as guidance here. So if we strike a gold, a feasible solution, we save massive efforts later. Okay, so what are the authors doing here? They are tackling mixed integer linear programming through optimization problems where some decisions must be integer. Think about things like choosing how many servers to activate or how to assign. So like we can't use fraction values like 2.5 or something. Traditionally, solvers explore solutions using diving heuristics. They try fixing one variable at a time and resolve the LP again and again. But this is often rule based and it's dumb, like always picking the most fractional variables doesn't work well in practice. So here's what L2 type changes. Instead of guessing, they train a graph neural network to predict good variable assignments based on past feasible solutions from similar problems. The model learns from good feasible solutions, those with low cost and valid assignments, then creates a probability distribution that favors solution with better objective value, and kind of like more stars to better solution. So when training, it tries to copy the distribution using a loss called the KL divergence to match its prediction with reality. So technically, the only train on divable variables that are not yet fixed are not slack unimportant ones. So okay, now I can take you to the next part. So I'll quickly go to the algorithm. It iteratively fix one at a time using LP relaxation of MLP. So I will just okay step by step break down what's given here. So we start at depth one. Okay, a d equal to one. This represents how deep we are diving in the tree, and then there is a loop. Here we pick a variable using a score function. This function scores all unfixed variables, and we pick the one with the highest scores, thinking of it like choosing the most promising variable to fix based on same heuristics. Once we pick the variable, we either fix it to its floor or ceiling value based on its LP. So we are trying both directions, rounding up or down. We update the LP relaxation in the line 6 here, if you can see, by tightening the bounds on variables J, and this essentially reduces our feasible region. Now we check if the updated LP problem is still feasible. If not, we break this. There's no point diving deeper. So it's if it's feasible, we solve the LP again to get a new relaxed solution. So the line 9th and 10th, if you can see, is a roundable, meaning it's close enough to integers. We round it and add the rounded solution to our candidate feasible set. Okay. Now next is our line 11 to 13. We update the depth and possibly update the set of candidate solution. The algorithm dives the search tree by fixing one variable at a time, solving LPs along the way, and checks if it's worth continuing. The clever part is the use of scoring function to decide which variables to fix, and this is exactly where L2 dive innovates. Instead of using fixed score, it learns the decision using GNN. This is trial and error loop. We keep fixing variables step by step, check if the problem remains feasible. If it does not, does and the solution looks good, we remember it, and if not, we stop and back up. Okay. So next, let's. This is the experimentation phase. What the author talked about. So author tested L2 dive, and what I personally took away from these experiments, they ran two separate types of experiments. One where L2 dive is used just for diving, and one where it's fully integrated into the branch and bound framework inside a solver. So experiment one, diving. With L2 type is first set of experiments, and the goal was to find a good feasible solution with a small primal gap. That basically means how close is our solution to the best possible one. Okay, then they use some synthetic benchmark problems from four different combinatorial families: set, cover, combinatorial auctions via facility locations, and independent set. L2 dive was trained separately for each problem type, used equal, which is MILP environment designed for learning. What I found really cool here is how consistently L2 dive outperformed classical heuristic like pseudo cost and line search for cost diving in both solution quality and stability. Looking at the table for set cover, L2 dive scored 55 versus the 3700 plus, if you can see here. For others, for combinatorial auctions, it got 222, again way ahead. Similarly, dominance in the facility location and independent set. So my learning L2 dive isn't just competitive, it's consistently smarter even when faced with complete new test instances. Now, in the second experiment, I will talk about L2 dive in branch and bound. Now, in the second experiment, they went a step further. Instead of using L2 dive only to get good solution, they embedded it into the solver's decision making during DNB. So now it's directly helps control the search process. Tested this on two real world problems: neural network verification, server load balancing. The results were super impressive. Let me break it down once. In server load balancing, L2 dive achieved a 25 to 30% improvement in primal dual integral over default settings. It also won 93 instances, while other barely won any. In neural network verification, L2 dive cut solving time by 20% and also won 287 instances, far more than others. So what I learned from this, I can give you some final thoughts. That is, this phases L2 dive is not just a proof of concept; it's deployable, efficient, and beats traditional methods even in real world industry use case. It also tells me the ML guided heuristics like this are the future of combinatorial optimization, especially when paired with robust solver like SEIP. Okay, let me so here's what we did exactly. So first we trained our GNN model from scratch. We used our MLP data, as I told. For every LP relaxation, we saved those features and learned from good integer solutions. Our loss dropped smoothly from 15.5 to 14.6. Then we used our trained model to do GNN guided diving, where we let the GNN pick which variable to fix next. Next, just like in paper, we plotted dive step versus objective, as you can see on the left. So here's where it gets interesting, and I think this is the smart part of our project. Initially, the GNN just picking the same variables, x83 and x72 again and again. Why? Because the training data had noise or was too similar. The GNN got tunnel vision. That itself was a signal we needed with better features, better sampling, and more diverse LP states. So we added features like reduced cost. With we could have I did add Slack with the different MILPL IP problems. The result GNN now did not pick different variables per step, but add the dive started, but it failed somewhat. But it did give me a good objective. But I was hoping for a better solution with the graph neural networks. So the practice of the Neuro IPS 2023 paper, Learning to Dive, is Branch and Brown proposed GNN based learning method that mimics how experts dive in MIP solvers. I implemented the same logic, starting with a clean heuristic dive, then trained my own GNN using extracted LP features. While our GNN dive matched the paper style, my model still needs better supervision, like the author used from real datasets, like a dataset. In my run, the GNN got stuck selecting the same variable again and again. So objective stopped improving, but that's where the insight lies. I think so. So that is like this. This shows that using features isn't enough. We need better training labels, more diversity in LP states, and probably even graph structures, like the paper suggested. Compared to this heuristics, which gave smooth improvement, JNN failed after 3 dives. So overall, the architecture works, our code replicates it, and the next step is plugging in better training signals. That's exactly what the author did with the massive training and evaluation with his data. So this is our result summary. Um, so this is the final conclusion by the author. I have already talked about it, and this is the reference. Thank you very much.